Hello again, welcome to chapter 9.7, Properties of Real Numbers. What we're going to start off with is one of my favorite laws called commutative law. And there are two versions of commutative law. One is for addition and the other one's for multiplication. For the first one, for addition, pretty much commutative law says if we have A plus B, that is equal to B plus A. Now, this is something you already know is true. So I'm going to give you an example. Let's say we have 1 plus 2. What is that? 3. So then we have 2 plus 1. Well, that's the same thing. It's 3. These two statements are equivalent. And that's what this law says. A plus B is equivalent to B plus A. They're the same. And the same deal applies to multiplication, where if we have A times B, that is equal to B times A. And we could see this play out with a nice example once more. For example, 1 times 2 is 2, and 2 times 1 is 2. Same thing. They're both equivalent statements. The next law we're going to tackle is Associative Law, in which it also has two versions, addition and multiplication. For addition, we have A plus B plus C, in which these parentheses around B plus C is implying to us that we should do them first, then add the A. And we say this is exactly the same thing as A plus B done first instead, and then plus the C. So to make life easy, we'll just pick a nice example. Let's say we have 1 plus 2 plus 3. 1 plus 2, I'm sorry, I said that wrong. We have 1 plus, and then 2 plus 3 we will do first, which is 5. And 1 plus 5 is 6. Now let's see if we messed with it. Maybe we reorder it where we did 1 plus 2 first, which I wanted to do beforehand for some reason. So now we have 1 plus 2, which is 3, and 3 plus 3 is still 6. So we still have equivalent statements here. They're both the same. So that's the associative law for addition. For multiplication, it's pretty much the same idea. Instead of plus signs, we now have multiplication symbols involved. And do notice it's all multiplication. There's no mix of an operation going on here. It's either purely addition or purely multiplication. That's why these two operations are so powerful in mathematics. They have these laws, and it makes them very, very nice for us to use. So we could see something really nice. Let's start with a nice example. 1 times 2 times 3. Which we have 1 times 2 times 3 is 6, and 1 times 6 is 6. It's just a quinkadink. It's kind of working out to be similar to the previous example. The next one we'll do is 1 times 2 first, then times it by 3. 1 times 2 is 2. 2 times 3 is 6. And we have equivalent statements. Our next thing we're going to talk about is like terms. I know it seems a little off. There is another law we're going to head to, but I feel that like terms, talking about them first, will make the next law seem much nicer to us. So like terms, let me give you an example of them, using the definition where we're saying the same variable to the same power. And your book has a little bit different of a definition. You could check it out. If we have, let's say, 5x, and we wanted to see what a like term to 5x would be, and I'll give you an example. So I'm using a comma to list off another like term. We could have negative 6x. We could also have, x, or 100x. All of these are like terms. It doesn't matter what's in front of the variable. What's important is that each variable here is exactly the same to the same power. So this is x to the first, x to the first, x to the first, x to the first. Alright, they like terms. Whatever's in the front is indifferent to us. Now, the next thing, coefficients. That's pretty much the thing in the front. So if I want to describe what the coefficient for 5x was, we'd say the coefficient is 5. If we want to describe the coefficient for this term, negative 6x, it's negative 6. It's whatever's in front of the variable for a single term, which these are all single terms. The challenging one is x here. You might be thinking, well, there's no coefficient, nothing's written there. But really, there's secretly a 1 times x there. There's a 1 in front of it, so 1's the coefficient. And then the nice easy guy, 100, is the coefficient for 100x. Now that we've tackled that out of the way, let's go ahead, let me go and do distributive law. So distributive law is a nice mix in which we have A times B plus C is equal to A times B plus A times C. So it's important for us to realize here that B and C are not like terms. Since we can't combine them, they're stuck in parentheses, and we don't enjoy that too much. We want to write this a different way without parentheses involved. So we take that A in the front and distribute it to each term, and that's where we have multiplication going on here, and addition, so 2 operations. A times the B, that's what's going on here, and then we also must do A times the C. Now, to show you how distributive law works, I'm going to give you a kind of a nice example. It's not type of problem we will see, it's just to make us feel comfortable with agreeing that the law is true. So if we have something like 2 times 1 plus 3. Now, we are trained parentheses first, so we would do 1 plus 3 first, in which we have 4. And then you have 2 times 4 is 8. To show you the power of distributive law, let's say for some reason we couldn't figure out that we had to do 1 plus 3 first. We can use distributive law to distribute the 2 to each term. And 2 times 1 is 2, plus 2 times 3 is 6. 2 plus 6 is 8. And we got the same exact thing. So that's why distributive law works. Now, factoring, it's not really a law, but it is something where we take something that's already been distributed, and there's not a nice example of this until later on, and we notice they have something in common, that A times B and A times C. So we want to undo it, so we'll take that A out. What's left behind is the B plus the C. And factoring is basically backwards, and that's what some people say, backwards distributive law. Oops, I can't spell D's. Distributive law. Okay, so let's go back to that like term business. It's very interesting. Distributive law does require us to be aware of it. So going back to those terms, let's combine like terms, because I said we couldn't combine B plus C, but let's talk about what we can combine. So let's say, for instance, our first one that we have here is x plus 10, x minus 15x. And we're asked to combine like terms. What we have to be aware of is when we combine like terms, we're going to combine the coefficients. And usually what I try to think of, the x or the variable, whatever our unit may be, I like to think of it as a unit. Instead of x, I'll say, okay, I have $1 here. Well, how many of them do I have? Well, $1, right? There's really a 1 out in the front as the coefficient. Plus, well, instead of x here, I'm going to call it $1. I'm going to say I have $10, because that's what the coefficient is telling me. I have 10 of whatever these things may be. And then I go and spend $15. That's what I'm pretty much treating the x like. I'm treating like $1. So 1 plus 10 is $11, minus $15 is I owe somebody $4. So instead of writing -$4, we're going to write -4x, because we just keep whatever the unit may be throughout, and we just combine the coefficients. So let's try another one. Let's say it's a little bit more long-winded. We have 3x minus 5y plus 8x plus y. Now, we have a little bit of different things going on here. We have x's and we have y's. So we have kind of like apples and oranges. Can't mix them. So they have to only be the same variable with the same variable. And there's only two x businesses going on here. We have 3x plus 8x. So when we combine these guys, we look at the coefficients. Whatever the coefficient is, that's how we're combining them. So this is really positive 3 plus 8. That gives us positive 11x. Now let's go to our y's. We have negative 5y. Whatever the sign is in front of the coefficient, that goes with it. So our coefficient is negative 5 here. Plus, and they forgot the 1 again, so we'll fill it in for them, 1y. Negative 5 plus 1 is negative 4y. And there's our final answer. So that's how we combine like terms. Let's go ahead and use distributive law now. And we'll see the power of it, because we'll have things, for example, like this. We have 3 times the quantity x plus 4y minus 2z. And my z has a line through it. So when we stare at this guy, we first want to simplify the parentheses, kind of like we did when I showed you distributive law and why it works. But we have an x, we have a y, and we have a z. They're not like terms, so we can't combine them. And we don't like the parentheses there. They make things very difficult for us. So to manipulate the equation, make it nicer, we use distributive law, besides the directions telling us to do so. And we take whatever's out front, whatever it may be, and you have to distribute it to each term. So x is a term, 4y is a term, negative 2z is a term. Each term must have that 3 distributed to it. So what we have going on here, and I'm going to write out the steps very long, we have 3 times x plus 3 times our 4y minus our 3 times 2z. And now we're going to try to multiply. 3 times x, well, that's just 3x, plus 3 times 4y, well, that's 12y, because 3 times 4 is 12, and y is coming along, minus 3 times 2 is 6, and z is coming along. Now, x, y, and z are still not like terms, so we can't combine them. So that is our final answer. Let's do one more. It's going to be a little bit different, using the same directions as above, in which we have negative 2 times the quantity x plus 3y minus 16z. Now, we have a negative 2 out front. That entire thing must be distributed to each term, sign and all. So we have negative 2 times x, which is negative 2x. Then we have negative 2 times positive 3y. That gets us negative 6y. Next and last, we have negative 2 times negative 16z. Negative times a negative is a positive 32z. And we still don't have any like terms, so we can't combine them, and that is our final answer. Alright, last but not least, we are going to go backwards. The directions ask us to factor. So that means we're starting with something, and we're going to be very nice with how we start. That looks like this. Maybe AS plus AT plus AR. Notice how everyone has an A. It's A times something. So we want to factor it out. They all have an A in common, so if we take out an A, we just need to fill in what's left behind, which we have an S plus a T, and I'm sorry my t's kind of look like plus signs, plus an r. And then we just have to close our parentheses, and there is our answer. If we were to use distributive law, we'd distribute the a to each term, and we'd get back what we started with. Now let's get a little bit more difficult. Let's say we have 3x plus 3y. So you notice maybe that they both share a 3. And they're not like terms, so we can't combine them or anything. If they were like terms, we want to combine them, but even our directions told us to factor. So we notice the 3's what they both have in common, factor it out, left behind is just the x plus y. And I said I was going to get a little bit harder. I think that was a little bit nice. So let's try one more. We'll make this one definitely be a little bit more difficult. It's not going to display as easily what should be factored out. Let's say we had this, 9m minus 45. Now, it's not clear to us we have maybe an m times something everywhere, because this guy doesn't have an m, or 9 times something, because this is 45. He doesn't really look like 9 times something. But maybe we could make it look like that. So, what I'm going to tell you, here's your clue. Look for the smallest constant, like 9. Versus 45. M is a variable. So I'm looking at the constant, and I'm starting with the smallest one. I can view this as 9 times m minus, and I'm hoping that I can write 45 as 9 times something. Well, 9 times 5 is 45. So there we go. There's our winner. That 9 is times something repeated. So we can factor out a 9. And left behind is an m minus 5. And if we were to do the distributive law, let's say we want to check ourselves, we take the 9 and distribute it to each term. So 9 times m is 9m. That looks like an A, it's a 9. 9 times negative 5 is negative 45. And it's exactly what we started with. And that is all.